So, hello everyone. My name is Fred, and I'll be your presenter for today. I am the chief architect at IBM's Spark Technology Center down on 505 Howard Street. I've worked at IBM for a while. I joined IBM from UC Berkeley in 2006, worked for IBM Research for 9 years, and since 2014 I've had my role at the Spark Technology Center. Just in case any of you are wondering what's a Spark Technology Center, we're an open source lab at 505 Howard Street in the Watson West building. We have a three-part mission. We contribute to the Apache Spark community. We build core technology and make it more enterprise and cloud ready. And we build data science skills and teach the enterprise about data science. And what all of that, those three-part missions generally break down to is writing a lot of code, pushing a lot of changes, in particular to Apache Spark, but also to related Apache projects like Apache Arrow and the Jupyter Notebook ecosystem, and as is relevant for this talk, Apache SystemML. So let's talk for a moment about what is Apache SystemML. And here we're going to hit our first slide where there used to be an animation, but I'll just talk you through what the animation was. So in a nutshell, Apache SystemML is about going from the linear algebra formulation of an algorithm expressed in a high-level language like R or Python, or with our latest API, Scala with Breeze-like matrices. And you take that matrix and vector representation, and instead of having to re-implement the algorithm to run on top of a system like Apache Spark, Apache SystemML makes that algorithm run in parallel at scale by translating it into a low-level execution plan. So before SystemML, if you have an algorithm that you've written in R in terms of matrices and vectors, you have to rewrite it in terms of, say, RDDs or data frames. And that means you write the algorithm twice, which is expensive. It's also error-prone because you write the algorithm twice. With SystemML, we have this nice big blue box where the algorithm goes in one side, the parallel execution plan that produces the result comes out the other. And what's inside that big blue box is a lot of advanced technology that was originally IBM research technology that IBM donated to the Apache Software Foundation in 2014 to create Apache SystemML, which is now a full-fledged Apache top-level project. So I mentioned linear algebra a couple times in that exposition. Let me just take a brief digression into why linear algebra, because linear algebra is really the language of machine learning. If you look at the paper representation of a machine learning algorithm, it's almost always in terms of linear algebra. Even the new deep learning algorithms, which are typically, you think of them in terms of tensor algebra, that turns into linear algebra as soon as you hit an actual implementation. And here's a quick example of linear algebra in action in the context of kind of the most basic machine learning algorithm, linear regression. So if you're looking at linear regression with an L2 loss metric, here's the formula at the top of the screen for your loss metric. You want to solve for W, your vector of coefficients, that's going to minimize L2 loss, the difference between your labels or your value, your target for prediction, and your features multiplied by that W, the vector of coefficients. If you set the gradient of this equation to 0, gradient being the linear algebra equivalent of a derivative, and solve for W, you get this system of normal equations. So we just need to invert this matrix and multiply by x transpose y, and we get our solution. And if you're writing in a high-level language such as R or Python with NumPy, you can translate this equation directly into code, or in a slightly more verbose form, this kind of 3 lines of code. So with linear regression and 3 lines of code, and this will scale reasonably well up to whatever fits on your laptop. In particular, these 3 lines of code, if you just type them into R, will scale up to the point where your original matrix X of features fits into memory twice as a dense matrix. And you can also fit the result A in memory at the same time. It works except when it doesn't, though, because if your features are sparse, all of a sudden converting them to dense will make you run out of memory. If the features are just too big at the outset to fit into memory, the whole thing's going to crash. If you can't fit 2 copies of it, it's going to crash. So generally speaking, when you take an algorithm like this, it's super simple until the point where you need to scale. And what SystemML is all about is taking this super simple representation and making it scale by picking apart that algorithm, looking at the pieces, rearranging them, constructing a parallel plan for executing those pieces, and stitching them back together again, giving you a result. And key to this is being able to look at the properties of the data, right? Because even though this is just 3 lines of code, you're going to run those 3 lines of code differently depending on what is the shape of X, what is the sparsity of X, what's the size of X. And you need to generate different execution plans depending on those data properties. So using data properties in a cost-based manner is another very important part of the SystemML algorithm. So at a high level, SystemML is about taking that linear algebra representation of the algorithm and automatically generating an efficient execution plan. And if you follow this approach, you can simplify the development of new algorithms because you can code at a high level and not have to re-implement the algorithm again to make it scale. This makes experimentation a lot easier. And key to this talk is as SystemML continues to move forward, the same algorithm code gets faster and faster and faster. We'll see an example of that at the end of this talk. So we got these 3 benefits: faster writing code, better experimentation, and faster, faster, faster. So that's SystemML in a very short nutshell. But for this talk, I'm going to focus not on what is Apache SystemML, but what is new in Apache SystemML. I'm going to focus pretty much exclusively for the rest of this talk on stuff that has been happening within the last year, year and a half. And there are 5 things here on the list. The first one I've already covered. Apache SystemML has graduated from incubation just this year. We are now in a top-level Apache project. As for the remaining 4, we have some significant improvements for our APIs for expressing those algorithms. We have a new technology called compressed linear algebra. We're using code generation in new and exciting ways. And we are starting to add some support for deep learning to the system. Let's move on to API improvements. So to write down an algorithm in SystemML, you're going to use R or Python syntax most of the time. So here we have an example of the subsets of R and Python that we support. And this example is doing a matrix factorization use case, in this case Gaussian non-negative matrix factorization, which is an iterative algorithm. You're iteratively solving for 2 factors, H and W. Those letters come from the German names for the factors. And you multiply those factors together, they will approximate an original matrix, which in this case is V. And so you can see how you can just basically copy and paste equations into either of these syntaxes. Once you have your algorithm expressed as this, you pass it through an API in a host language, R, Python, Scala, and are supported as host languages, although R is going through a third-party project right now called R for ML that we're working on folding into SystemML. So those are the stable APIs for accessing SystemML. We've made some big improvements to the ML context, which is kind of like a SQL context in JDBC that you use to pass in these algorithms to SystemML. But another cool thing that we've done, which will be very interesting for any Scala people in the audience, is that we now have an experimental Scala DSL. This is still something of a proof of concept. We have a PR and a branch where this is implemented, but it's not folded into mainline SystemML. But I have some links here which will be in the PDF, in fact the PDF that I'm presenting right now, that you can look to download offline, or you can search for that work item number 1353. The basic idea here is, again, here we have matrix factorization, in this case with a Poisson noise model, implemented in this Scala DSL. And this is all Scala code that's going to be all native to your larger Scala program. We have this keyword up here, SystemML. That's basically a function that takes as its argument a block of code. And that's going to use a toolkit called Emma to walk the parse tree, walk the AST of that code, and generate our own internal representation of the program, and then return a function that you can call later on, or rather an object that you can call the run function on later on, that will look at the runtime characteristics of the input data, recompile that AST, and generate an efficient parallel execution plan. Some really cool stuff done by a gentleman from Germany called Felix Schuler. who was working at the Spark Technology Center at the time. Now, all these APIs I've talked about have been for algorithm development, and one experience we've had with users of SystemML is for every algorithm developer, there's going to be 5 or 10 people consuming that algorithm. So with the recent releases of SystemML, we've worked a lot on new APIs for consuming algorithms, and in particular, we have APIs for compatibility with the pipeline model in scikit-learn and Spark. So here's a quick code example of how this works. On the left-hand side of the screen, we have code that we've copied and pasted from a NumPy example on the scikit-learn, NumPy-based example on the scikit-learn website. You don't need to read all those lines of code. The key thing to note here is you change these 2 lines on the right. And now this example is using SystemML to do linear regression. We could do the same thing with Spark. You have a Spark example from Spark ML pipelines. You change 2 lines of code, and now you're using SystemML to do scalable logistic regression on top of the same Spark installation that's doing all the data transformation parts of your pipeline. So those are our API improvements. Next on the list is compressed linear algebra. How are we doing for time, by the way? We're good? OK. This is deeper into the engine now. We're getting into the core of SystemML, some of our newer optimizations. Compressed linear algebra is a concept that we have been working on for about 2 years now. And the idea is when we implemented a bunch of algorithms, common algorithms on top of SystemML, we noticed a pattern occurring over and over again in these iterative machine learning algorithms, where you have repeated memory-bound access to basically your lightly transformed training data as you iterate to try and find the best model. Here's an example, linear regression, same problem as we showed earlier, but this time with the conjugate gradient method, which is able to handle a larger variety of loss metrics. In this case, you're iterating over the input data x and constantly recomputing a new gradient. So this pattern occurs over and over and over and over again in lots of different algorithms, this repeated access to the large training data. And making all of these algorithms scale is all about making that training data that you're going to be running over and over again fit in memory. It runs fastest if it fits in memory on your master node on one machine. It runs almost as fast if you can fit it in aggregate cluster memory. And as soon as you go out of aggregate cluster memory, performance gets progressively worse. You have to switch to an out-of-core implementation. So what we do in SystemML is we use compression, lossless compression, to make that training data that we're iterating over smaller. So it's going to fit in memory of the master node for longer. It's going to fit in memory on the nodes of our Spark cluster for longer. And even when we get beyond this point where the compressed data fits in memory, we can still stream it from disk a lot faster because it's compressed. Now, if you just did this naively and gzipped your matrices, it doesn't really work, because the overhead of decompressing that data is more than the overhead of a lot of the operations you do directly over the training data. Not only that, but general purpose compression techniques tend not to do well with data that came out of a database, and a lot of data that you run machine learning on came out of a database. So instead, what we do here is we borrow techniques from database compression and extend them with some new techniques that we've developed, so we can compress the data very highly, and we can do all these core linear algebra operations directly in the compressed domain. So that gets us the much better compression and much better performance compared to just naively using gzip, to the point where we can go much faster than running over uncompressed data. So to give you an idea of how things can get faster with compression, some operations that you would do on matrices and vectors are basically orders of magnitude asymptotically faster in compressed data because they turn into metadata operations. Here we have an example of the performance of squaring all the cells of a matrix, very common task if you're computing a loss based on squares. Run over 1, 2, 3, 4, 5, 6 common machine learning data sets. The blue bars are how long it takes to run over the uncompressed data. The green bars are how long it takes to run when the data is compressed. And you'll notice the absence of green bars. That is because all the other green bars here round down to 0 pixels high. So you need to switch to a log scale to actually be able to see that difference. And this is happening because if you're using a dictionary-based compression technique to encode the data in the matrix, squaring all the values in that matrix is just a matter of operating over the dictionary, not the actual data. So long as you have repeated values, every repeated value can be squared at once. Now, not every operation you would want to do in the context of a larger algorithm is going to have this property. And of course, because of Amdahl's law, whatever is the least accelerated operation is going to be the gating factor here. So we've gone through and done a comprehensive look at all of the fundamental kernels we have in SystemML, and we have optimized all the important ones so that they run at scale on compressed data. Here's a particularly interesting one, matrix vector multiplication. So multiplying a matrix by a vector on the right. This is a very challenging operation because it's very data intensive. But as you can see, we can get this running at comparable speed directly over compressed data compared with running it over the original uncompressed data. When you take all these kernels and combine them together with our optimizer, we can generate compression and execution plans that make end-to-end algorithms, in this case training an L2 SVM, run anywhere from 5 to 26 times faster. And this performance, across, by the way, a wide variety of data sizes. This performance benefit, again, comes from the fact that we can fit the data in memory of the master node a lot longer. We can fit the data in the memory of the worker nodes for longer when it still spills out of the master node. And when we go to an out-of-core implementation of the algorithm, we're streaming data from SSD a lot faster because it's compressed. And you'll note, by the way, that these numbers are including the overhead of compressing the data. To make an apples-to-apples comparison, we start both the compressed and uncompressed runs with the data in uncompressed format on disk. So that's compressed linear algebra in a nutshell. The next new thing that we've added to the SystemML project is code generation for the purpose of generating fused kernels. So what's a fused kernel? One thing I didn't mention when I talked about linear regression in 3 lines earlier on is that this first line with that multiplying the matrix by its transpose on the left, that's the key one for performance. It's also one where the way you would do this naively, if you just type that code into R, is not at all optimal because you don't want to actually have to materialize that transpose if you're just going to throw it away. It turns out you can compute the value of this expression in a single pass without materializing that intermediate result. And SystemML includes a fused kernel and will pattern match and use that fused kernel to make this operation go much, much faster, particularly in cases where X is stored striped across multiple nodes. And we have a number of these different patterns that were built into the system, and the optimizer would pattern match against them. Here's a more complex example. This pattern occurs a lot in matrix factorization use cases, where you have a matrix W that you are trying to approximate with the product of 2 factors, U and S. And in each iteration, you are solving for one of the 2 factors. In this case, we are solving for U. And the important intermediate value to compute here is going to involve multiplying the existing factors together, multiplying that cell-wise by the original matrix we're trying to approximate, and then multiplying again by the transpose of one of the factors. If you did this naively, you would be materializing this product here, which is not a good idea because that is dense and W is sparse. So this is typically orders of magnitude larger than any other data structure in this algorithm. Basically, you're going to fail even on trivial data sizes. However, you can do this entire operation in a single pass without materializing that intermediate if you have a fused kernel that does this entire expression in one pass. Basically, you walk over the cells or the blocks of the output matrix, computing those blocks. And we pattern match in our optimizer on whenever we see this pattern, we substitute in the kernel. And that works quite well for a wide variety of algorithms. The trouble is if you had like one additional variable included in this expression, you can get out of the space that our pre-built kernel covers. So what we're doing now in SystemML is we dynamically generate these fused kernels. The way that we do this is we start by analyzing the internal representation of that program that we have broken down into a directed acyclic graph that's a data flow graph. We augment it with additional information for costing. We generate potential options for what operators we're going to fuse into new fused kernels, use a cost model to estimate how fast those fused kernels are going to run and how much memory they're going to require. And then we make a choice and we generate new code from scratch for the fused kernel, compile that, and link it back into the original DAG of operators. So some very cool stuff. We have some more detailed technical documentation that I'll link to about exactly how this gets done. But the upshot is, if you include this in the system, we can make end-to-end algorithms run in these numbers either just as fast or faster than with the original hand-tuned kernels. And the hand-tuned kernels were tuned for these particular algorithms. So our new code generation was able to find opportunities to go faster than what we had tuned by hand for the particular algorithms. And you can imagine for new algorithms that we hadn't tuned those kernels for, it's even better. And there are actually newer numbers under submission now, currently embargoed because of that, where every algorithm gets faster with the new code gen because there are always little fused kernels that we hadn't considered when we were doing this by hand. So hopefully we'll be able to talk about that the next time I talk about this, but look for that paper coming out hopefully in VLDB next year. So we talked about code generation, compressed linear algebra, improvements to our APIs, becoming a top-level project. Now on to the last topic, deep learning. How much time do I have for this? 5 minutes, great. So SystemML started out as a project in IBM Research in 2009. And back then, deep learning was not on very many people's radar. We were focused initially on more, you could say, traditional methods of deep learning, making those scale, making those customizable. But in the last 2 years, many members of the SystemML team have been focusing on how do we make SystemML extend to deep learning algorithms. And again, the idea is, as I said before, we want to bring the benefits of this approach, simple algorithm development, system gets faster, your algorithm gets faster, to deep learning. Now, key to that is having a library of deep learning kernels, and because we have linear algebra as our core API for accessing the functionality of the system, we were able to build up a library in a very short amount of time. Basically, Mike Dusenberry, who's sitting right back there, one of our committers, put this library together in like a couple months of part-time work with a very extensive set of kernels. And this went so fast because we have a high-level representation of these kernels. A 2D convolution, which is many pages of code in C++, is about 5 lines when you're doing it with matrices. On top of that, for pre-built models that you may have created with other toolkits, we have an importer, which can at this point import Caffe and Keras models and generate code in our domain-specific language to train or score the model. And we also have an extension to our pipeline API to be able to incorporate SystemML running a deep learning model in the context of a larger data processing pipeline. Now, that's the development of the algorithms to make them actually run faster. Well, the code generation I just talked about is helpful in that, but another thing that's helpful is GPU support, being able to run in particular convolution operations on GPUs. And we have a GPU accelerated backend now. This takes advantage of the pluggability that was designed into SystemML from the start. We designed SystemML to be able to handle both SMPs and scale out architectures like Spark. So we have a pluggable backend. We're adding 3 new pluggable backends for single node, single GPU, single node, multiple GPU, and multi-node GPU. We have a lot of kernels that are already implemented for these backends. And if you look at and step back at what the impact of these changes have been to our deep learning performance, we're still not at the point where we can compete performance-wise with systems that were purpose-built for deep learning, but it's getting a lot closer. If you look at a particular use case that some of my colleagues in research are working on involving inference for a large-scale image segmentation model, starting at SystemML 0.14, which came out earlier this year, the performance running without GPUs has already gotten almost twice as fast running the same code because of improvements to the optimizer, code gen, use of native BLAS routines. And with the GPU kernels, we get an additional performance boost. So we're overall about an order of magnitude faster now, and this continues to move forward. So talked about deep learning, code generation, compressed linear algebra, API improvements, and our being a top-level Apache project. And if you want to try all of these new features out, in addition to that core, you write in terms of linear algebra and out comes a fast algorithm aspect of SystemML, you can get SystemML today from either systemml.apache.org to download and install. If you want to just try out a pre-installed version, IBM is hosting that on the IBM cloud. You can go to datascience.ibm.com and just try it out without having to install Spark. I also have links here to some more detailed technical documentation about each of the topics that I've talked about today, if you want to find out more. Yeah, please take a picture. This will also be in the PDF. So thank you very much for coming to my talk. Apologies for the delays here. And thanks to the SystemML team, because this has been really a team effort. Many people working over many years to produce this system. Thank you.
Some questions?
Do we have time for questions?
You can take a couple questions.
Okay, great. Any questions from the audience? So the question is, what happens when you add compression that uses linear algebra to represent the intermediate data in the algorithm? And that's a very important question with a very deep answer that we go into in a great deal of detail in our VLDB paper. The short answer is you need to work pretty hard to be able to compress matrix data fast and still get good compression. And we did a lot of work on sampling techniques to be able to quickly pull out a sample of the data, determine how to compress a matrix, and then compress it very quickly. And we were able to get things to the point where in all of our end-to-end experiments, we're including the compression overhead, and we're still 5, 10, 20 times faster.
Oh, you already
yes.
improved that part.
Now, one caveat here is this technique, the compression, is primarily for traditional iterative algorithms where your chief overhead is access to that training data that's stored in memory. In deep learning, we're still working out that story. We have different ideas involving compression, but those are going to be more about sparsity, and that's ongoing work. So, great question. Thank you.
Any other questions? So, thank you for the talk. My question is about the deep learning module. I was curious if you're developing the computation graph and using auto differentiation in the background, or doing it numerically, the differentiations.
The question is, are we doing a numerical differentiation or automatic differentiation? We implement the differentiation, the backward pass, in our high-level language. So that library, that neural network library I showed you that Mike back there wrote, includes the backprop as the computation of the derivatives. There's no auto-differentiation currently in the system, but because we have that high-level language, we can write down the gradient computation in a very compact manner. Now that means if you add a custom operation, you do need a custom derivative, but at least you can write that in terms of linear algebra. So, great question, thank you.
All right, that's what we've got time for. Thanks, Fred.
Okay, thank you very much.
Roll with the punches, AB, this is your talk.